Hello students. Okay, in last topic we have discussed the force acting on the charge particle inside the magnetic field. Okay, and now our today's topic is that force on a current conductor placed in a magnetic field. What happened to the current carrying conductor when it is placed inside the magnetic field? Now let us consider a conductor having length L and it is placed inside the field, and field makes angle theta with the direction of the current, and the direction of the drift velocity of the electron is here, and this is the theta, the angle between current and the field. A is the area of cross section, and according to Lorentz we have the force acting on is given, any charge given by Q B cross B. Okay, B cross B. According to them, here the Q is now the total force acting on one electron is given by minus E. Vd is the velocity of the electron and B is the field of the electron. So net force acting on one electron is given by F equal to minus E Vd cross B. Clearly, and if we know the total number of electron in the conductor, then we can calculate the total force acting on the conductor. Okay, for this we have now consider the n number of electron per unit volume. Small n is the number of electron per unit volume. Then the total number of electron, it is the product of n into volume. Here A into L is the volume of the conductor. So total number of electron is given by NaL. This is the total number of electron. This is the force acting on one electron. Then to find out the total force, we have to multiply these two factors. So N into F, we get minus NaLe Vd cross V. This is the total force acting on the conductor. Now also, from the drift velocity and current relation, we know I equal to minus NeaVd. Okay, this is the relation of the drift velocity and current. Okay, now from this, here we have Nea also Vd. Okay, now put the value of I here. These terms we get F equal to IL cross B, okay, or ILB sin theta. This is the net force which acts on the conductor whenever it is placed in the field, and also it carry current I. So it is ILB sin theta, or it is I in vector form, it is IL cross B. Also special case, if theta equal to 0 degree or 180 degree, that is the field makes angle theta with the current. The direction of the current is here in this direction. Also field flows in this direction. Then sin theta, here sin theta becomes 0, sin okay, and force becomes 0. That is, whenever a conductor carrying current is placed inside the field and it is placed in parallel direction to the field, then no force acts on it. And what happened if the angle makes 90 degree? Then what happened? Here the field is in this direction and current flows in this direction. The angle between these two is 90 degree. Then sin 90 equal to 1 and force becomes maximum. It is ILB or IBL. It is the maximum force acts on this conductor. This is the total happening. That is whenever the conductor placed in the magnetic field carrying some current. Now, if we make some rectangular coil of these conductors, then what happened to this? Then torque act on current carrying coil. Now we make a rectangular coil A, B, C, D. Okay. Now this coil is placed inside the magnetic field, and Now it is clear from the diagram that field flows in this direction and the coil is placed at this angle, making angle theta. Okay, now total force due to this phenomena, this is, if we consider the whole coil with some 4 conductors A, B, B, C, C, D and D, A, then the net forces F1 act on DA, F2 act on BC, F3 act on AB and F4 act on CD. Now, to find out the force F1, here we have formula IBL. Here I is the current flowing through this conductor and DA is the length and B is the field. Now the total angle between current and the length is 90 plus theta. Here theta is this normal, theta angle with normal, and total here this is 90 degree. So total angle between DA and B is 90 plus theta, and F1 becomes IDAB sine 90 plus theta, and this becomes IBB cos theta, because DA is the breadth of this coil and L is the length of this coil. So we have IDAB sine 90 plus theta or IBB cos theta. BB is the breadth and I is the current, B is the field. This acts in upward direction as shown in the diagram. Similarly, here F2, here sine 90 minus theta. So it also becomes IBB cos theta. It becomes downward, upward force and downward net cancel each other because these forces act in opposite direction. Now, what happened to other sides AB and CD? Here the angle between current and field is 90 degree. Also current and field is 90 degree. So here IABB, the value of AB is L, so it becomes ILB. Due to this theta equal to 90 degree, sin 90 becomes 1. So now this force acts toward the reader, and here the direction of current is changed, so the force act on this side is away from the reader, that is this acts toward the board, this is in the outward direction, this is inward, this is outward. Due to this whole coil is rotating in this direction, because due to these two forces which acts on the body in opposite direction, these forces equal and opposite forces making at some distance, then this constitute a couple, or the turning effect of this couple is called torque. This torque can be calculated either force into perpendicular distance between these two forces. Okay, the F3 and F4 acts in such a way that they constitute a torque, and the perpendicular distance between them can be calculated easily by this. This can be calculated as B sine theta, because this length is here, it is B. So by trigonometry this can be calculated as B sine theta. So put the perpendicular distance value here, B sine theta. Now L into B, this becomes area. So IAB sine theta, or torque can be written as IA cross B. Also we know that I into A, this is net magnetic dipole moment. So torque also can be written as in the form of M cross B. So at the end we conclude that if we place a conductor carrying current inside the field, it experiences force ILB sin theta or IL cross B, and if a coil with area A is placed inside the field, it experiences a torque that is given by I A cross B. I A cross B. Okay. Thank you.